你说哦，现在的 Y 也是那个满面，有找不到，有人
OK， 好嘞。
上到他们的那个群组，那个 link 点进去，他们就可以直接编辑，就是他们找他们的名字，然后后面 email 帮我
写上他们的名字。
他们已经有，就是我从那个点名单里面直接把他们的名字全部都放到那个表格里面，他们就找他们的名字，后面有一栏是 email， 帮我把 email 填上去。
OK. This gentleman asked me a very, very good question. So, where are you going to upload your testing file, your examination report? Where are you going to upload? Good question. Okay. So TA has passed a message to our line group. Okay. So everyone, please go to that line group. Let me see. I'm not quite sure what that is. All right. So there is a sheet, okay, in our line group. So please find your name, put your email after your name. Okay? Don't change your classmate's email. Don't do that. Just go find your name, your own name, and put your email. Put your email after your name, okay? And then, okay, so why do we need this? Two purposes. One purpose is this. After this coming Friday, this coming Saturday, this coming Friday, TA will email you the address of Google Drive. In the Google Drive, everyone has a file folder, and then 除了每一个人的 file folder 下面会不会放 exam 1, 2, 3？
不会，只是把全部的东西都丢进去。
下次怎么办？下次考试的时候怎么办？
我会把他们的那个资料改分析，会变成空的。对。
这样。Okay. All right. So TA will email you the address of the Google Drive. And of course, you need the email. You need the your email address so that you can get into that Google Drive, right? So you will find the name of you will find your name in the Google Drive. Then you upload all the necessary files to that file folder. Okay, that's the way you upload your examination results. In the problem sheet, I will tell you when we are going to close the Google Drive. If we close the Google Drive, for example, if I usually close the Google Drive at noon on Saturday, for example. Okay? If I close the Google Drive at noon on Saturday, so TA will close the Google Drive. 你们两个 miss 掉最重要的信息。你等一下问一下那个，我不知道重复，你们两个这样你们会考试会完蛋。我不知道重复哦。 So Tia will close the Google Drive at the exact time I requested on the problem sheet. So then you will no longer upload your files after that time, okay? So please make sure you upload all the necessary files before the deadline, okay? What if I give you 4 problems and you don't have time to finish all problems? Say, for example, you have finished 3 problems. Please remember, still upload the files, because if you fail to upload the files, you'll get 0. You'll get 0. All right? Very, very important. You have to upload whatever you have done. Whatever you have done. You have to upload you have to upload whatever you have done before the deadline. Okay? Maybe you think that, I only solved 2 problems, and you feel that there's no hope. So you decided not to upload everything before the deadline. Then you are making a very wrong decision, because maybe most of the students, most of your classmates can only solve 2 problems also. So you might be you might get a high score in the class. So don't be shy, okay? So if you, no matter how much you have done, just upload it to the Google Drive, okay? So the second purpose I need your email is that I will use the email you have provided to the sheet. I will use the email and email you the score, your score. Okay. This is the only way I tell you how much you get for the exam. All right? So please write in your email address. Any question? Is everything have you done that? Have you done that? 你上去了吗？可以吗？ Okay, good. Okay, so now for this. Oh, by the way, sometimes I will give you this kind of question. Sometimes for this kind of question, this is a calculation problem. Okay, you have to calculate sigma mu by programming. You also have to do some calculation to calculate x1 and x2 based on the ABC, right? So it's not necessarily true that the examination is programming only. Sometimes I will require you to do some calculations, something like this. Okay? For this, you have to do programming to find sigma, mu, and then you substitute all those sigma and mu into those 3 equations. Those 3 equations, you'll get ABC, and based on the ABC, you'll get the solution x1 and x2. Why do we need x1 and x2? Let's see this. For px given c1, this is Px given C1, this is Px given C2. If they have equal variance, in other words, sigma 1 equal to sigma 2, then there you will see if sigma 1 equal to sigma 2, this term is 0. So there is only, so this is a linear equation instead of quadratic equation. For this is, if this is linear equation, then there is only one solution. So see, the primary point here is here. Only one point, right? With sigma 1 equal to sigma 2. So for this sigma 1 equal to sigma 2, for any x to the left of this boundary point is class 1. For any x to the right of this boundary point is class 2. For example, if x is here, you will have PC1 given x greater than PC2 given x. You miss a very important message. You ask him, tell him. And for this, for x greater than this boundary point, you see, PC2 is given greater than PC1. So this is, so any x greater than this boundary point can be classified as class 2. Any, let's say this is class 1, this is, so let me change the statement. The red line is class 1, the blue line is class 2. So any x greater than this boundary point, as you can see, PC1 given x is here, PC2 given x is here. So apparently this value is greater than this value. So x can be classified as class 1. And for any x less than this, for example here, PC2 given x is greater than PC1 given x. So x can be classified as class 2, something like this. Okay? This is for sigma 1 equal to sigma 2. Again, sigma 1 equal to sigma 2. The quadratic function becomes linear. Quadratic equation becomes a linear equation. For linear equation, there is only one solution. Okay? So you know how to do it. You know how to solve this linear equation. Now, what if PC1, Px given C1 like this, okay? And Px given C2 like this. From here, you can see sigma 1 is greater than sigma 2, right? The distribution is wider for class 1, and this is Px given C2 is this. So for this sigma 1 greater than sigma 2, according to this equation, there are two solutions of this, right? So you will be able to solve two boundary points. One is here, the other one is here, right? So from here you will see that to the right of this first boundary point, we have PC1 given x greater than PC2 given x. So this can be classified as class 1. For the x to the left or smaller than the second boundary point, we have PC1 given x greater than PC2 of x still can be classified as class 1. So any x less than second boundary point or greater than first boundary point can be classified as class 1. And any x between first and second boundary point, which is here, can be classified as class 2. So if you are going to write a very simple source code to do the classification, you, based on the training data, you are able to calculate sigma 1 and mu 1. sigma 2 and mu 2. And then you will be able to calculate ABC. And then based on ABC, you will be able to calculate two solutions. This, you only need to have two solutions or two boundary points. And then based on this, you will see that based on those two boundary points, we are able to do classification for two classes, for two binary classes. That is easy to do, like this. And what if we put some rejection? See, if there's no rejection for this problem, if there's no rejection, any point greater than this first boundary point, this is class 1, and any point less than second boundary point, this is class 1. And any point between boundary 1 and boundary 2 is class 2. If we add some rejection, do you remember? If we have some rejection, you have to be the PC1 of given PC1 given x or PC2 given x has to be very, very large, so that they can be classified as class 1 or class 2, right? Otherwise, it has to be rejected. It has to be rejected. So from here, this is a typical example. You see, PC2 given x. See, as long as you have PC2 given x greater than 0.5, if PC2 is slightly greater than 0.5, then PC1 given x will be slightly less than 0.5. As long as we have the x that is a little bit to the right of the second boundary point, it can be classified as class 2. But now, if we put some rejection here, your PC2 given x has to be much greater than 0.5. Maybe, for example, it has to be much greater than 0.7 or something. Then it can be classified as this. Otherwise, it will be rejected. Similarly, PC1 for here. Similarly, PC1 is the same thing. PC1 given x has to be very much greater than some value, otherwise it has to be rejected. This is how we do. You can, well, here it's, you can consider this as PC1 and PC2, or you can consider this as a risk, R of alpha I given x. We have gone through this. So, I'm thinking about it. I might also give you some problem that requires to calculate the rejection. You can try this at home. Okay. This is the expected risk. Do you remember what is the expected risk? Look at this, chapter 3. See, R alpha I given x is defined as this. This is equal to 1 minus PCI given x, which is easy to calculate. You know, I hope that you now understand how to, now you know how to calculate PCI given x. And for the risk to reject this is equal to lambda. lambda is the value I assign. This, okay? So in order to do calculation, see here, in order to do classification, you have to have R of alpha I given X less than this. And R of alpha I given X less than, this is lambda, less than lambda. You have to have both conditions to satisfy. Otherwise, it has to be rejected. Okay. This is the situation we are looking at here. See, we have to have first R of alpha 1 given X, R of alpha 2 here. R of alpha 1 given X greater than R of alpha 2 given X. Also, the R of alpha 1 given X has to be greater than R of alpha 3 given X. R of alpha 3 given X is the rejection, which is lambda. So in other words, the risk has to be R of alpha 1 here. This is, see, the class 2 is somewhere here. This part, only this part. The figure was not drawn too well. See, this is, oh, sorry, this is class 2. Okay, let's say class 2. It has to be greater than some value instead of greater than 0.5. Okay? Otherwise, it has to be rejected. So, if I ask you to do rejection, then you have to follow those two decision rule. Okay? Any question about this? All right. Now, we have gone through this regression, right? So I will skip this. Again, I will, please remember the equation of coefficient of determination. For example, in some problem, I might ask you, I might not ask you not only do the regression, I will ask you to calculate the so-called coefficient of determination. Now you should know that coefficient of determination is the square root of 1 minus ERSE. ERSE is defined as this equation. Okay? This is what I just tell you the examination report format. In the third part of the examination report format, I will ask you to write down the answer to the problem to the question I will ask you. This is a typical value I might ask you to calculate. Maybe this, maybe ERSE, maybe coefficient of determination. And so for regression to be considered useful, R has to be as close to 1 as possible. In other words, ERSE has to be as close to 0 as possible. Why? This. ERSE is equal to this. This is your regression result, right? This is the training given this is RT is from training data. So this is the real answer. This is the answer you have calculated. And then you can calculate this R bar. R bar is the average value of the given this. So this this ERSE is calculated, important. ERSE is calculated based on training data, right? You will have RT. Based on the training data, you calculate ERSE, then you calculate coefficient of determination. If your capital R, coefficient of determination, is a little bit far away from 1, then you know that your training result is not too good, right? Then you should come up with a different approach. Do you understand? So, so based on the capital R, the value of capital R, you should be able to decide whether you are going to use your proposed regression function or not. I might give you a very nonlinear data like this. Then you have to guess what kind of, see, because for regression, you have to guess this. You have to guess g of xt. And based on your proposed function, g of x, you are required to calculate wk minus 1 up to w0, right? But if your proposed polynomial is not accurate enough, you will have your coefficient of, you have COD, coefficient of determination, far away from 1. Then you know this is, your guess is not correct. Then you might use trial and error to find, to try some other function, okay? Because I will simply give you the data. I will not give you the polynomial. You have to guess the polynomial. Okay, do you understand what I'm talking about? I will simply give you data. What is the order of polynomial? I will not give you, I will not tell you. So you have to try. Okay? So for regression problem, I suggest you save more time to do that, because you have to use trial and error to finally try a right model. How do you know your proposed model is correct? It is based on this R. Okay? And if you don't like capital R, COD, you can also use this, or this, or this, or this. I have told you before, last week. So, but COD is good to use. We know that, see, this is this E is expectation. Expectation of R minus G of x given x this is the mean square error. We have already known that mean square error here see, mean square error is equal to mean square error here, d minus theta. Theta is the parameter you have to estimate, and d is your data, and theta is the parameter you want to estimate. So eventually you will have this, d minus ed squared plus ed minus theta. Variance plus square bias, right? So in terms of regression, it's like this. Training data, this is the expectation of your model. So this is given x, this is plus e of r given x minus g of x. I'm sorry. This is the mean of the data. The data, mean of the data plus mean of the data minus your proposed regression, g of x. So what is this? The first term, r minus er given x, is a noise. Why? Look at this. If r is equal to r is the given data. R is the data I give you. Actually, it is the real data, which is f of x, plus some noise. So expectation of r given x is equal to, this is the noise, right? And f of x is the real answer. Real answer, there's no random variable here. The randomness comes from the noise. So expectation of r is equal to expectation of f of x, which does not have randomness. So e of f of x is equal to f of x, and plus e of epsilon here. So r minus er given x is equal to this one plus this one minus this. So you have epsilon minus e of epsilon. And if you take e of r minus er of x squared here, you will have expectation of epsilon minus epsilon squared. And epsilon minus epsilon squared is this is the noise. This is the mean of the noise. And so this is the variance of the noise. So this is called sigma epsilon squared. This is the variance of the noise, which is what we mean here. This term. This term is the variance of the noise. So if you take expectation mean square error, the mean square error of the real data minus the model here, the first term is the variance of the noise. And why is variance of the noise? I have explained to you here. Okay? And plus this term is the square error. So this is the mean of the data minus the model. Okay? Square. So this is the square error here. And if we can make very good regression, g of x will be very close to e of x. This can be reduced. But this one is the variance of the noise contained in the data. It can never be reduced. It's not possible to do this. So this one is not possible to be reduced. This one can be reduced if you make your regression better, then you will have smaller square error here. Okay? And this, don't forget, this term can never be reduced. The data I give you for the exam I will intentionally put some noise in the data. So that's why no matter how hard you have tried, it is not possible to have the zero mean square error. It's not possible because you can never reduce this term. This is the noise contained in the data. Okay, and for IoT, the noise comes from the environment or come from device noise. So it can never be reduced. And if you look further, if we look this term, if we look into this term further, we see that for every time you run your regression, you'll get different answer, different g of x. You'll get different g of x. So if you run 100 times, you will have 100 g of x. So in order to make this square area smaller, you can, if you have a bunch of data set, you can use different data sets. Take the expectation. This expectation now is no longer taking noise as noise as the random variable. We are taking the noise as we are taking the data as a random variable. So this is E of Ex. This Ex is different from this E here. Take Ex of this term here. You look at this minus Ex of this. Then you look at bias of this plus square of the bias here, and the variance of this term here. So you will see that if we could take the expectation or take the average of your g of x, you can reduce this term, but you cannot reduce this term because this is the bias. So always, the first term is unavoided, and the second term, variance, can be avoided. So so what does this mean? It means that okay, for example, this term. The first time you run your regression, you get data like this. The second time you run the same model. Second time you run, you probably get this. The third time you get model like this. The fourth time you get the model like this. The fifth time you get a model like this. So you have G1, G2, G3. Well, this G1 is not discriminant function, it's the regression function. G3, G4. And G5. So you run 5 times, you get 5 different answers, 5 different g of x. What can you do? From this term, it tells you that if you take the expectation of all the possible g of x, it is possible to reduce this term. What does this mean? It means that if I get 5 different answers, then I will say, oh, the model I'm going to use is this. this is how we take the mean, right? How we take the mean. So this is supposed to be your answer. It is very possible that for some difficult problem, you will get different answer every time you run your regression. And every time you run your regression, and you get the results regression function not very close. So what can you do? You use this. You use this instead of simply you simply use G1 or G2 or G3 or G4 or G5. Either one is not good enough. This one is the best. Why? Because this one is close to E of G of X, right? This is close to this. So if our G of X is almost equal to EX G of X, then this term can be almost equal to 0. We can reduce this term. See? Remember? If G of X is almost equal to EX G of X, then the second term can be reduced to almost to 0. Then we can reduce the variance of this. And this is the way we do. So if you're going to design a chip to do the regression, and if you find that, every time you run this, you are totally different, not totally, very different GI of X. So what can we do? What kind of G of X you should put into the chip? The answer is this. This is how we define here. We use this. Because if G of X is equal to this, then the variance can be reduced. This is also good for multivariate model. It's not only for univariate model. It fits all. The next topic I'm going to tell you is this. Look at this. If I give you a bunch of data, the real f, the real function, f is the real function. The real f is this blue line here. For your regression, you might use linear model. This is the linear. You run several times. Every time you run, you get the linear model like this. And then you take the average. You take the average. This is the red line here, G bar, right? G bar is this. So this can be considered as G bar of X, right? And this is trying to be. We hope that G bar of X is almost equal to this. Right? So if you run several times, you take the average of model, you get this red line here. But this red line is, as you can see, is very different from the true answer, which is the green F here. And if this is not good, I hope if you are in this situation, I hope that by calculating the COD, coefficient of decision, you might be able to know that, the linear model is not good. Then let's say we use third order polynomial. You get third answer, and the average of those 5 blue line is the red line here. This one is okay. And what if we are not clever enough? We want to use fifth order polynomial, which is this one. And you can also use 10th order polynomial, whatever you want. Okay. For the regression, I would like to tell you that some theory here. What is variance? What is variance? What is variance of your regression? The variance of your regression, usually we can use this. If I ask you to calculate the variance of your regression function, this is the one we use. You see, this is g r of x, right? And this is g bar of x. G bar of x is defined as this. And then this is a t is 1 equal to 1 to n. I'm sorry, I should make it like, let me make it like n. Okay, n here. n is the number of times I try this. So the variance of G according to this equation, I hope you understand, this is equal to this. This. And g bar of x is equal to I equal to 1 to n. Right? So you will get, oh sorry, xt. If I write this, can you understand? Can you understand how to write a very simple computer code to do this calculation? I hope you understand what I'm talking about. What? What? I don't understand. What? To loop, right, to loop, right, to loop. To loop, double loop, to do this. Yeah, so, yeah, that's right. So, the expectation, the least square error, which is defined as expectation of g of x minus f of x, it is always equal to square of bias of g plus bias of g. Square of, and what is bias of g? Or the square? Square of bias of g is defined as this. This is square bias, this. And this is the variance. And this, the variance, again, this square bias here cannot be reduced, but this one can be reduced. If we put more effort to calculate g of x n times and take the average, actually, this is like this. And then the value here is this. Right? Okay, so let's take 10 minutes break. I'll come back.